we'll talk about what causes motion. First thing we should be familiar with is mass. Mass, besides being 1 hour of torture for me every Sunday, right, is amount of matter that makes up an object, right? So mass pretty much measures how much matter the object possesses. Okay, mass quantity does not change whether you bring it to the center of the earth, to top of the mountain, or even if you bring it to the different planets, the mass does not change. Okay, the amount of inertia an object possesses. So mass quantity also measures how much inertia. Now this word is pretty new, inertia, right? That word inertia means nature's laziness. Okay? And I'm going to explain that to you about more how much nature's laziness it possesses. Okay? More massive an object is, more inertia it possesses. Okay? So mass is inertia. Greater the mass, greater the inertia. Okay? For example, an 8 kilogram mass has twice the inertia of the 4 kilogram mass. Okay? Mass is a scalar quantity, so it does not have any direction, and it's not a vector. The symbol for mass will be lowercase m. Don't get that confused with the unit meters. Okay? When you see this m in a formula, it means mass. The unit for mass are given as follows. In physics, we use MKS system, which means meters, kilograms, seconds, and our mass is measured in kilograms. Chemistry people like to use smaller things, so they use CGS system, which is centimeters, grams, seconds. Okay, so chemistry they use grams, but in physics and we use kilograms. Kilograms is about a little more than 2 pounds. Okay. I don't know if you guys can see this. I don't know if you guys can actually hear. It's pretty cool. This is a kilogram. This is one. Pretty cool, huh? Yeah. So if you were to, you know that, right? That's pretty massive. You think of it, right? I should show this to those La La Land people, the virtual world kids. Would be awesome, right? This is a kilogram. Now, the people in class they're feeling this. They're like, whoa, whoa, that's pretty massive, right? So this is a little more than 2 pounds, right? Now again, 1 kilogram is a mass. Pound, believe it or not, is actually a weight. So we'll talk about that more in detail because in British system, mass is measured in slugs. We're not talking about those slimy creatures that come out after a rain, right? We're talking about slugs, I think, as in like a size, like a cannonball. Maybe like when you get shot, you get slug embedded in your body. That's kind of slug is what they're talking about, I think. It's a pretty big unit. I think like one slug is like close to more than 30 pounds. So it's pretty big. Okay. So inertia, let's talk about inertia. Inertia, okay, so mass is important. This is very important. Inertia is also important. Right? So inertia pretty much is the amount of resistance to motion. I'm going to also say or rest. Okay? So object can be in motion or it could be at rest. Okay. So how much resistance to motion an object possesses? So if object is at rest, it wants to stay at rest. It doesn't want to move. When object's in motion, it wants to stay in motion. It doesn't want to stop. So whatever the state that object possesses at that moment is what that object wants to be at. Nature's laziness. It doesn't want to change. Okay? So inertia is quantitative, which means it's a numerical value that can be measured. Okay? And that measurement is the mass value. So if an object is, it should be at rest, right? It should be at rest. The object's inertia is a measure of how much it wants to stay at rest. So for example, let's say we have an elephant. This is not anything political, by the way. It just happened this way for some reason. Let's say we have an elephant and we have a mouse, right? Now, obviously, elephant is a lot more massive than a mouse, right? So if an elephant is sitting down on a skateboard and a mouse is sitting down on a skateboard, it's so much easier to change the state of mice at rest than elephant at rest, right? Because elephant has a lot more inertia than the mouse. Similarly, if an object is moving with constant velocity, the object's inertia is a measure of how much it wants to maintain its current speed and direction. Now, because it is velocity, it has to have both components, speed and direction. Right? So when an object is in motion and it's moving in a straight line, it wants to stay moving in a straight line. So when you see an elephant on a skateboard coming at you, I don't think you want to stop that thing because there's no way you're going to be able to stop that elephant coming at you on a skateboard because it has way too much inertia. However, if you see a mouse on a skateboard coming at you, it's probably a lot easier to stop that mouse because it has less inertia. Okay, that elephant's going to just plow right through you and just continue on. Right? All righty. Now we talk about forces. Force, right? May the force be with you, right? Force is any push or a pull, right? If you push on something, you're applying force on something. If you're pulling on something, you're applying force on something. It is the thing, and the thing is in quotes here, that causes acceleration. We know the word acceleration. So this force, any push or a pull can cause objects to accelerate, which means it could cause objects to change its velocity. This is a very abstract concept because we can't really see the force, right? We can't really touch the force. We can't taste it, smell it, right? But we can only see the effects of force. So if it's happening to you, you can feel the force, right? If somebody's pushing you, you can feel it, right? When somebody's pulling on you, you can feel it. So you can feel the force or you can see the effects of the force, but you can never touch it, hear it, see it, taste it, smell it. All right. So you can see the effects. That effects is the acceleration. Okay. So for example, an acceleration caused by gravity. You can see objects accelerate towards the center of the earth when you drop something because the gravity, the force of gravity will pull the object towards the center of the earth, which will cause it to accelerate. When you acceleration of the baseball due to a bat, when a bat strikes the ball, not only it changes the velocity of that ball, but it also changes the direction. Well, then you're changing velocity too, I guess, right? So because it changes the velocity of the ball, which is speed and direction, is causing that ball to accelerate. So acceleration of a car due to friction. Without friction, your car would never be able to move. It's the friction between the road and the tires that's going to make your car able to accelerate. Okay? So those are some examples of effects of force. So when you exert or push or pull on an object, you say you are exerting a force on that object. Right? Forces cannot be seen, cannot be tasted, cannot be smelled. So they're only known by the effects they cause, and that is acceleration. Here's the first effect of force. Force causes acceleration. But, there's a big but right there, right? If a car is stuck in the mud and this giant owl-faced, bloodshot-eyed, rat-tailed monkey, right, pushes or exerts a force and car doesn't move, there's no acceleration. Is he still exerting a force on that car? Amy? Yeah, right? Wait, are you Amy? Okay. I could only see your eyes, so I can't really. All right. So yes, yes, of course. But why isn't it accelerating then? Why isn't it accelerating, Amy? I think car has plenty of inertia. It's at rest. So, you know. Now don't forget, it is stuck in the mud. So you said the monkey is definitely applying force on this car, right? So this is force on the car by the monkey. Now it should accelerate, but it's not. What's causing it not to not accelerate? The mud. Mud must be pushing which way? In the opposite direction of monkey's push. Yeah. So the mud is canceling out, right, the force, right, on car by mud. This force is force on car by monkey, right? Well, these two forces are canceling each other out, so my net force is 0. Okay, so okay, so it's the net force that makes objects accelerate. Okay, okay, it's the net force that causes objects to accelerate. All right, so Newton had many laws, like if you're a scientist, you'd be lucky enough to have just one law named after you, but he had many. And out of those many, here are three laws of motion that he decided to publish. The first law of Newton's law of motion is law of inertia. Again, the word inertia we should be familiar with. It's nature's laziness. It's a measure of nature's laziness. Or mass, right? It's also mass. So according to Newton's first law, he stated, an object will continue in its state of rest or constant velocity. There are two parts to this. Okay? Rest or constant velocity, unless that object is acted upon by some outside external net force. Okay? So he said when object's at rest, it's going to stay at rest unless some external force acts on it. And when object's moving, it's going to move at constant velocity, which means same speed in a straight line, unless some external force acts on the object. So there are two parts to that, right? Objects at rest wants to stay at rest, and when object's in motion, it tends to stay in motion in a straight line unless it is acted upon by some external net force. So the net force is defined as sum of all forces, just like that monkey and a car and a mud problem, okay? The sum of all forces, and since forces is a vector, right, it has to have directions, okay? The Greek letter uppercase sigma means sum of. You should know that from math class, right? So sum of all forces. And forces are vectors is equal to the net force. Okay? Again, this is sum of all force vectors. If the net force is equal to 0, then acceleration must, there's no negotiation here, must also equal to 0. Okay? So if the net force is equal to 0, then acceleration must also equal to 0. This is a change from Aristotle's belief that a body's natural state is at rest. Aristotle thought, when a rock falls from the side of a cliff, it's going to actually roll down and it's going to keep rolling, and then eventually it's going to find this natural state and it's going to, here it is. I'm going to rest right here. And that's, he thought, was the way to go. He also thought heavier objects fall faster than the lighter objects. Lighter things will rise, like smoke and dust will rise, but rocks will fall. Okay, so that is a completely different view than Newton has introduced. Newton said, no, not necessarily. When object's in motion, it's going to want to stay in motion. And when object's at rest, it's going to want to stay at rest. So there are two parts, okay, which is completely different than Aristotle's view. They believed Aristotle for more than like almost 5,000 years. Anyway, so Aristotle basically is wrong. Here's a question for it. Can an object have forces acting on it and not be accelerating? Aaron, what would you say? Can an object have forces acting on it and not be accelerating? Yes, absolutely. Give me an example. Yeah, right? Car in mud, right? So basically, when net force is 0, right? there are, right, other forces, right, that adds up to zero net force. Therefore, if the net force is zero, then the acceleration is zero. What about number two? If an object has zero net force acting on it, does that mean the object must be at rest? Jason, what would you say about that?
I would say no, because it just means it's not accelerating, it's still the velocity.
Excellent, right? It just means it's not accelerating. You're absolutely right, right? So, right? Okay, I hope that makes sense, right? If an object is already moving at constant velocity, there's no net force acting on it, right? But it is still moving, right? Alrighty, let's talk about Newton's second law. Newton's second law is quite simple. First law was law of inertia. The second law is F equals ma. Okay, F equals ma. Well, he didn't really just say F equals ma. He said, well, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. That's the way he explained it. Okay? The direction of acceleration vector will be in the same direction as the net force vector. So this is the way he actually described it. He said the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. So acceleration is net force divided by mass. Now, if you multiply both sides by mass, this mass will cancel out and this will become ma. That's how they got F equals ma. The unit of force, right? And since force is equal to mass times acceleration, the unit of force is going to be kilograms times meters per second squared, right? Because mass is measured in kilograms times meters per second squared. So they decide to give this derived unit in honor of Sir Isaac Newton, and they call that Newton. Must be nice to have your name named after a unit. You know, I want to do the same thing. You know, I want to have my name as a unit. Like, I want to introduce metric circle. Screw that 360 degrees. There should be 100 kims in a metric circle. So in one complete circle, there should be 100 kims, right? Come on, we should start this change.org and have some petitions signed here, right? Come on, it makes perfect sense, I think, right? If it's 50 kims, you're 50% of the circle. Well, mind blown, right? Screw all that irrational number of taus and 2 pi's. 100 kims. That's what I want. All right, all right. Maybe next life. I don't know. We'll see. So inertia, okay? Inertia can also be measured using this concept. So if I were to apply 10 newtons of force on two different objects, right? So if I apply 10 newtons of force in the positive x direction to 10 kilogram object and 100 kilogram object, right? So 10 kilogram object will be like a little toddler. 100 kilogram object will be like a lineman in NFL, right? Or maybe like a linebacker. Not linemen are, they're like 300 pounders, but like linebackers are like more like, 220s, right? 240s. So if I were to apply 10 newtons of force to a toddler versus 10 newtons of force to a NFL lineman, let's say, and they're both on a skateboard, the toddler will accelerate at 1 meter per second squared, where the lineman will only go 1/10 of meter per second squared. So because the acceleration is lower, matter of fact, 10 times lower than the toddler, this lineman, offensive lineman, will have more inertia because it has less acceleration than the toddler who's only got 10 kilograms of mass will accelerate at 1 meter per second squared. Does that make sense? All right. So you can measure and quantify inertia by measuring their accelerations applying same amount of force to two objects. All right. So remember that an acceleration is inversely proportional to the inertia of an object. Therefore, mass 2 must have 10 times more inertia than mass 1 because it has 10 times less acceleration than the mass 2 or mass 1. All right. All right. Third law of motion. So his first law was inertia. Second law was F equals ma. The third law is action-reaction forces. Okay? So when one object, so this is important that you have to understand there are two objects acting on to each other rather than two forces acting on one object. They're two different things, right? Instead of, like, if I have this, instead of two forces acting on one object, there are two objects, like one and my fingers is the other, right? So there are two objects, one is my finger and one is this mass, and there are two objects acting on each other, okay? So my finger is acting on this mass, and the mass is acting on my finger. Got that? Instead of left finger, right finger acting on one mass. Okay? So when one object exerts a force on a second object, that second object will exert a force on the first object. Okay? So there are two different agents happening. There are two different agents. The second force will be equal in magnitude, but in opposite direction of the first force. The exact same amount, but in opposite directions. So force always comes in pairs, okay? Using the on and by terms, It's very important. So let's take a look at this tray held up by this hand. Okay? The action force will be force exerted on the tray by the hand. Okay? Is the action. And the reaction force will be the force exerted on the hand by the tray. Reaction. Okay? They are same amount, but in opposite directions. Right now, your butt is acting on the chair, right? So the force on the chair by the butt is your action force. The force on your butt by the chair is your reaction force, right? The chair is acting on the floor, right? So the force acting on the floor by the chair is action force. The reaction force is the force on the chair by the floor is the reaction force. Does that make sense? All right. So you have to learn how to identify that. Right? You have to learn how to identify that correctly. Now, some other forces. This normal force is force by the surface onto the object. Okay? So force onto the object by the surface, right? By the table, right? Table surface. So normal force is this is actually a perpendicular force, right? Surface force, actually, perpendicular force by, well, we should make it on the object by the table. Okay. The reaction force is N prime is also a perpendicular force, right, on the table by the object. Okay. So there are two normal forces happening. Normal force caused by the table onto the object, as well as no normal force caused by the object surface onto the table. Okay. Common misconception that people have is the normal force are action-reaction pair with the weight. That is not true. And we'll explain that later more in detail. So weight and normal force are not action-reaction pair. Okay. Normal force and normal prime is action-reaction, but not the weight. Another pair of action-reaction would be this object will have weight caused by the gravity pulling on that thing. So the weight of this object is force on object by Earth will be the weight. The reaction will be on Earth by the object. So as much as the Earth is pulling on this object, the exact equal amount of force is acting on the Earth by this object. So they're both pulling on each other equally, but in the opposite direction. Similarly, you know, here is our Earth, right? Our blue planet, right? Here's the moon, right? Earth gravitational pull, right? It will pull the moon, right? So Fg by on moon by Earth is exactly the same as, right, force G of on Earth by the moon. Okay? So gravitational pull for Earth to moon are going to be exact same value, but in the opposite direction. Okay, any questions so far? All righty then. Continue on. So a little bit more of action reaction. Okay. So according to Newton's third law, when an object falls to the earth, there is a force exerted by an object on earth, right? It's obvious the earth is pulling onto the object, and by reaction force, the object is pulling on the earth. It has to be there, right? It has to be there. Then how come we can't see the earth accelerate towards an object every time I drop something? Shouldn't Earth go back to the object just as much as the object come down to the Earth? Right? So every time, like, in fall, when apples fall from a tree, the Earth should be going up. Does that truly happen? And the answer is, it actually does. but it does. Earth does accelerate towards the object that's falling. It does. But that when we calculate that, right? So we say this force of gravity here for the apple, right, is equal to, let's say, Fg, right? And the force of the earth being pulled by the apple is also same amount, Fg. Okay? We can calculate this Fg by measuring the mass of this apple and measuring the acceleration of the apple, right? So we know that this is equal to the mass of the apple times the acceleration of the apple. Let's say the mass of the apple is like, I don't know, let's say it's a big monster apple. It's like half a pound or half a kilogram, 1 pound apple, right? So 0.5 kilograms for the mass of the apple, let's say. And we know the acceleration of this apple. The acceleration is 9.8 meters per second squared. So this force is approximately 4.9 newtons. Okay? So half a kilogram apple falling towards the earth at 9.8 meters per second squared, okay, will have 4.9 newtons of gravitational force acting on the apple by the earth. Well, guess what? That apple is pulling on the earth exact same amount, 4.9 newtons. But here is the apple. Mass of the apple is 0.5 kilograms. Acceleration of the apple is 9.8 meters per second squared. And we knew that that was 4.9 newtons. Well, that has to be true for the Earth and the acceleration of the Earth. The mass of the Earth is 6 times 10 to the 24th kilograms. That times the acceleration of the Earth. Do you know how big this number is? This number is right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oop, a little too much. 24 freaking zeros, right? So my acceleration for Earth is equal to 4.9 divided by, that is like trillion times smaller than Microsoft Zero. You know what Microsoft Zero is, right? If you're a programmer. If you ever use like spreadsheet, like Excel, your answer is supposed to come out to be exactly zero. But sometimes Microsoft gives you like 6.33467 times 10 to the negative 16th instead of zero. Well, that's even smaller than Microsoft Zero. It's going to be, so Earth does accelerate, Amy, but it's not, you just can't see it. It's just immeasurable almost. It's negligible, okay? That's why you don't see the Earth going up. But it technically can be calculated, I guess. All right. Alrighty then. Let's take a look at this silly goat. Okay, let's say this silly goat has to be pulling this cart, and this cart actually has a very, very tiny nanoscopic wheels down at the bottom that is frictionless. All right. So we asked this goat to pull on that cart, and a goat refuses to pull. You know, the goat said, "No, I'm not pulling this thing, because I went to Harvard, and Harvard taught me that Newton's three laws, right? And according to Newton's third law, when I pull on this cart, that cart's going to pull me back with equal and opposite force. So action-reaction pair is going to cancel out, which will give me net force of zero. And if net force is zero, then the acceleration has to be zero. Therefore, this cart is at rest. And since it's at rest, it's going to stay at rest according to the first law. So according to Newton's three laws, I shouldn't even pull this cart because it's not going to accelerate. And if it's already at rest, it's going to stay at rest. Is the goat correct? If goat is correct, then nothing will ever move in this world. Right? How can you reason with this goat? Is the goat correct? Ben. Why not? Wait. Let me put you on our screen so we could all see you. Yo, look at that. Jeffrey, man, that looks really disturbing. This is what I have to deal with every day, guys. Like I only see this. I see this. I see Ben's face once in a while. But when I have to write a recommendation letter, like, yes, this person had a circular face and it had initials in the center. Well, Jeffrey had very angry eyebrows. Anyway, I'm sorry. Go ahead. Uh-huh. Ah. Repeat that. Absolutely. The goat has to apply the force onto the ground, right? And what happens then? Outstanding. That's correct. That's correct. And that was a really hard concept to understand for people back in the 1700s. It just did not work out. It's like, well, I don't get it, because if there's action and reaction, nothing should ever move, right? But that goat is actually applying the force onto the ground. So when the goat is applying the force onto the ground, so this is the force on ground by goat, and the reaction force is the ground applying force back onto the goat, equal and opposite direction, force on goat by ground. So this is the friction that's actually pushing the goat forward. And the box just follows. Now, if this box is filled with rocks, the acceleration of the whole system will be very small. If the box is empty, the acceleration will be much greater, right? So think of it as if this goat was on ice. You're right, that's the next ice capade, goats on ice. That'd be pretty cool, actually, right? If this were all ice, even if the box wasn't attached to the goat, right, that goat's going to be like, it's not going anywhere, right? Similarly, if I were to have my car, right, on the ice, and if I floor it, my car's just going to spin out and not go anywhere, right? It's the friction between the wheel of the car and the road that pushes your car forward. That's why you need a good set of tires. Yeah. So imagine, like, if I had a tug of war between two groups, right? And if I tell you those two groups, you could probably predict who's going to win. Like, one group is varsity football players, right? High school football players. And the other group is going to be middle school orchestra. Don't laugh. Well, you guys are laughing. You guys are laughing. Orchestra kids are mean. They're like, yeah, badass. You know? Well, but I didn't tell you that I'm going to put the football players on a sheet of ice, right? Barefoot. And I'm going to give middle school orchestra kids a rubber floor with spikes. Now you know who's going to win, right? You get the point, right? So the kids are actually applying force onto the ground, not onto the, right? I mean, obviously they're going to have to hold on to the rope too, but then when they pull on those guys, they're going to slowly accelerate towards the orchestra kids, all right? To the cello player. All right. Hopefully that will illustrate some visuals that can actually help out with your anchor. Now, here are some important common forces that you need to know, okay? Obviously, we are governed by this thing called gravity. We will never escape it as long as we are on any planet, okay? Gravity is basically an attractive force between two objects, which we will learn a lot more in detail when we get to chapter 15. That's the last chapter you'll be learning from me this year. Well, then again, some of you are actually going to stay behind, and we'll learn some special relativity too. But gravity is pretty much a force between two masses, attractive force. And because they attract, it would cause an object to accelerate towards the other object. And force of gravity on Earth is calculated by multiplying the mass in kilograms times the acceleration of that, which is 9.8 meters per second squared. Okay? So the acceleration due to gravity, right, is equal to negative 9.8 meters per second squared y hat. Now, why y hat? Well, because gravity sucks. It sucks towards everything in towards the center of the earth, right? So even for people in Australia, it will be sucking down towards the center of the earth. Therefore, it is down for them as well as for us in the northern hemisphere. It's down towards the center of the earth. So everybody's going to be, right, being like pulled towards the center of the earth no matter where you are on the earth. That's why it is negative y hat. Okay. On moon, it'd be different. The acceleration due to gravity on the moon is only 1.67 meters per second squared towards the center of the moon. Okay. So this force due to gravity is also known as the weight. So your weight can change depending on which planet you're on. However, your mass will not change. Okay? Your mass will never change, but your weight can. Okay? So if you want to lose weight quickly, all you have to do is go to the moon. It'd be pretty intense, you know. So like if you weigh 100 pounds now and if you go to the moon, you only weigh about like 17 pounds or something like that. That's pretty good, you know. That's pretty good. Maybe I should start a scam. Like, want to lose weight quickly? You know, send me money now, and I'll show you exactly how you can lose weight. Right? I'll just show them how to lose weight, but I'm not going to actually, right? Go to the moon or just orbit. Then you'll be weightless. You know? Technicality. I like that. So here, you know, make sure you understand the direction. Okay, it's always negative y hat only. Okay, straight down to the center of the earth. Okay. It doesn't matter even if you put this thing on an incline, like a ramp or something, the weight will always pull straight down in the y direction, in the negative y direction. So even if this thing is on a slant like this, your FG will always go straight down. Okay. Your weight will never go sideways. Okay. Your weight will always go straight down. Very, very important. And next, we're going to talk about the normal force. Now, the normal force is very important because you need to understand the normal force in order to calculate friction. Okay? Now, normal force is a surface force of a table, the ground, right? Desk, floor, etc. It is straight up 90 degrees from the surface. Right? That's why it sometimes is called the perpendicular force. Perpendicular force. Okay. Now, if it's on a horizontal surface, your F normal is measured how much force has to support this object so that it doesn't fall through. Okay? Now, if there's only an object there with no other external vertical forces, then your FG in this case happens to be same as your F normal. Okay? Your F normal does not always equal to the weight of the object. Why? Imagine normal force as, if I were to put a bathroom scale right here, does your bathroom scale always measure your weight? Yeah? Amy? Next year when you go to college, you're going to be sharing a dorm room with your roommate, and you're standing on a bathroom scale, and your roommate decides to play a little trick, sneaks up behind you, grabs you by the shoulder, it's like, oh, you got such a pretty hair, right? And then pushes you down, right, from the shoulder. And then you read your bathroom scale. Is it going to read your weight? No. It's going to actually read the normal force that you are applying onto that bathroom scale, right? So when you look at it, you're like, oh my God, I'm going to, cut down on my carbs, right? Well, next week, your roommate decides to be friendly, right? Instead of pushing you down by the shoulder, she grabs you by the elbows and lifts you up slightly while you're standing on the bathroom scale. Now you're like, oh, so psyched, right? Right? Now I can eat all the ice cream I want, right? See, so the bathroom scale doesn't truly measure your weight, it measures your normal force. Does that make sense? Yeah. So keep that in mind. I think I always like to make these crazy stories so it visually sticks into your mind so you don't forget it. So in this case, if I were to place like let's say I put it like a hand and then push down on this thing, right? Just like your roommate did on you. Now, if I push down on this thing with extra force down, right, as F push, now my normal force is going to spike up, right? Just like your roommate pushed you down from your shoulders down, right? So your normal force does not always measure your weight, okay? So think about normal forces, though, if you're putting scale between the surface of each other and what the bathroom scale would read, okay? So normal force is a reactive force, not proactive. So if I push down on it, it's going to react to that. If I pull up on it, it's going to react to that. So normal force will react to whatever the force is acting on the surface. If I put this object on an incline like this, now my normal force is going to actually be different than the weight, obviously, because now my normal force becomes the component of my weight, Fg. Okay? So here, since my normal force has to be perpendicular to the surface, right? This surface does not have to completely support the weight of this object because it's at an angle. Okay? Well, how do I figure that out? Well, if I were to draw this incline, and here's the incline like so, and let's say this incline has angle of theta. Well, we know this is Fg, and Fg will always point straight down towards the center of the Earth. So this here is the Fg. Okay? Your Fg can be broken up into its component of Fg perpendicular and Fg parallel. I drew my FG perpendicular a little too long. So here's my FG parallel. Now what does that mean? This parallel means it's parallel to my incline. So this FG is parallel to my incline. This F perpendicular is perpendicular to my incline. Now, what would happen to this object if I were to like put something on an incline and just let it go? What would happen to this? Aaron, what would happen to this object if I just let it go? It would slide down, right? Would this thing slide down as same as if I were to drop something, or would it be less? Less. It would definitely be less. Instead of 100% of my FG making this object accelerate straight down, it would only be this parallel component making it accelerate down like this. So I always like to take it to the extreme. Imagine if I were to place this on an incline like this shallow, and I put like a bar of soap right here. Nobody uses bar of soap anymore. I guess they're all liquid now, but that thing would slide down very slowly, right? Right? Where if I put it like here, and then I put a bar of soap down here, like, right? Then if I do it like this, it's just gonna just fall straight down. Does that make sense? Right? So this action of sliding down, which will accelerate along the incline, will be caused only by the FG parallel. This FG perpendicular will be exact same value as my F normal going in the opposite direction. So this will be my F normal. So my F normal value and my FG perpendicular value will be the exact same values. Okay? So how do I calculate that? Well, this theta right here, and if I were to extend this FG straight down, this is a right triangle. So this angle here has to be a complementary angle of my theta. Does that make sense? Right? Well, isn't this right angle right here, because this is perpendicular to my surface, so isn't this complementary angle same as my angle theta? So this has to be my theta. So now I proved it, we can always use it. Because this here is a right angle right here. So is everybody okay in the virtual land? Yeah? You guys following me okay? All right. Therefore, since this theta is up there and this is the opposite, this FG parallel is hypotenuse FG times sine of theta, because it's the opposite of my angle theta. And sometimes this is also known as FGX. So don't get confused with X and say, oh, it's FGX, so it has to be cosine. No, it's sine. Okay? And FG perpendicular is also same as FG times cosine of theta. And sometimes this is also known as FGY, because we would rotate our axis, where the incline parallel would be x-axis, perpendicular to the incline will be the y-axis. Okay? All right. Any questions? All right. I know that's a lot, right? So the normal force is very tricky. What would happen to my normal force as I increase my angle from here like this, what would happen to my normal force? Nothing? My normal force will stay exactly the same? What if I have my normal, like if I have my object here, what would my normal force be? It'd be same as the gravity. Does that make the Fg, the weight of it, right? That's correct. John, you have a question? Now, what would happen as I increase the angle? What would happen to my normal force? It decreases to zero. When is it 90 degrees? Because, right? Cosine of 90 is zero. All right, so my normal force would decrease as my angle approaches to 90 degrees. And it will get to zero eventually. Okay? So F normal is always perpendicular to the surface, and that's very important. Perpendicular. That means it's 90 degrees, all right, from the surface. In most cases, my F normal, most cases, not always, most cases, right, is equal to FG perpendicular. In most cases. If there are any other forces acting on this, like this way, or you know what I mean? If there are any other additional forces acting on the object, whether this way, this way, this way, then it's not going to be the case. Okay? So you have to watch out for what other forces are acting on this. If there are no other forces, only gravity is acting on it, then F normal is FG perpendicular. Okay? Not always, in most cases. F normal is not always equal to the weight, so make sure you understand that. We talked about that, right? Amy and Amy's roommate, right? It may be increased or reduced by the third force acting on the vertical plane. All right? All right. My voice is shot now. My throat is like starting to hurt. All right. Friction. I think this is where we got up to until like the principal came in the other class. So friction is a surface force, and this is actually parallel to the surface, unlike the normal force. The normal force was perpendicular, where friction is parallel to the surface, and it resists the tendency for sliding. So the frictional force is a reactive force, and that's so important, not proactive, okay? So it's going to actually react to whatever the push that it experiences. So for example, if I place this, I am pushing onto this, but it's not moving, it's not accelerating. What's holding it back? What's holding it back? Why isn't it accelerating? I am pushing, but it's not accelerating. Come on, Marin, why isn't it accelerating? Friction is holding it back. It's canceling out my push, right? Right? Let's say I can calculate the friction of this using this equation. Friction is equal to mu times F normal, right? Well, let's say I calculate this friction to be 50 newtons. I'm just making this number up. And I'm pushing this with 30 newtons of force. Will it accelerate? What's my acceleration here? Come on, what's my acceleration? Somebody. I'm pushing with 30 newtons of force. Is it going to accelerate when my friction has to be, let's say, maximum of 50 newtons? No, it will not accelerate. So my acceleration is 0. So what is my frictional value? Even though it is calculated to be 50 newtons, I'm pushing with 30 newtons and it's not accelerating. So what's my frictional value? What would you say? 30. Because it is a reactive force, it only requires 30 to keep it from accelerating. Now I'm pushing with 40 newtons. Can you see that? 40 newtons. It's still not accelerating. What's my frictional value now? Oh, come on. This is so hard. 40. Right? 40. Now I'm doing 49.99. Is it accelerating? No. What's my frictional value? 49.99 newtons. Now I'm going to push with 50 newtons. Did it accelerate? Yes. What's my net force? My net force. I'm pushing with, right? I'm pushing with 60 newtons. My frictional value maximum can only have 50, right? So what's my net force? 10. 10 newtons, correct. 10 newtons, right? So frictional value can only react to whatever the force that you're applying on it. But when it reaches beyond the threshold, then it stays there, okay? So this mu right here, what is this mu, John? Well, this mu is a lowercase Greek letter m. It represents coefficient of friction. And this coefficient of friction, right? Think of this mu as pain, right? Higher the mu, higher the pain, right? If you like lather up with like soap on the mirror in the bathroom and then you rub your face on that mirror, would it be painful? No, it's like nice and smooth, right? Low pain, low mu. Now let's take that same face outside sidewalk, concrete sidewalk, right? Place your face against the sidewalk and then rub. Does it hurt? Yeah, high mu, right? So if you have like, vulcanized rubber on concrete, that's like tire in the road, right? High mu, right? Metal blade on ice, low mu. Oh my God, class is over. All right, have a wonderful day. I'll see you guys on Thursday, I guess. Not you guys, but other group, right? All right.